The screen is visible. Is the screen visible? Can someone please confirm?
Yes,
Visible.
yes.
Okay. Okay, so we'll start. Good evening, everyone. I am Shomodip from Department of Engineering at Indian Institute of Science. I will be handling this daily sessions for the course NPTEL course Advances in UHV Transmission and Distribution. Today is the seventh week. One more class is this is the penultimate class, and one more class is left after this. Next Saturday, we will be wrapping up the course. So these sessions are generally meant for clarifying your doubts. Basically, this is a tutorial session, and these are meant for clarifying your doubts if you have anything pertaining to the course, which is being handled by Professor Subbareddy. So what I do is generally I'll take some new students are there I think today. So I'll give a brief intro, then I'll start. So we take up some important topics from the course, like we had talked about numerical computation of electric field. Then we had looked into the some of the numerical techniques of electric field computation, and then we had moved to audible noise, calculation of audible noise, sound pressure level, the detection, the circuits for detection of radio interference voltages, how RIV is generated, and all those things we have looked into. So first I'll give a quick recap of what I had discussed in the previous class, and then I will move on to today's class, today's topics. Okay. So we were actually discussing about grounding in the previous class, the different types of grounding, like substation grounding, in which I had talked about the grounding mechanisms for different kinds of signals is different. It depends on the frequency of the signal, right? For power frequency, the frequency is 50 hertz, and we have the wavelength. And we have the wavelength in the order of 6,000 kilometers, whereas for impulse signals, which are very high frequency signals, we have much lower wavelengths. So we were talking about electrically thin wires, right? So a wire is thin, we can say it in two perspectives. One is geometrically thin, other is electrically thin. So what do we mean by geometrically thin? Geometrically thin basically means if the diameter of the cross section of the wire is less than a particular value, then we call it as a geometrically thin wire. Whereas electrically thin means it has a different perspective. So we need to see whether the length of that wire is a considerable fraction of the wavelength of the signal that is propagating. So suppose I have given an example here, a 10-meter wire and a 100 hertz signal is propagating through the 10-meter wire. Whether that 10-meter wire should be treated as electrically thin or not. So a 10-meter wire, the wavelength of the signal propagating is like if the frequency is 100 hertz, we can find out the wavelength of the signal, which is around 3000 kilometers. So from that, we find out what is the ratio of L by lambda. So L is here 10 meters and wavelength we have found out. So we see the ratio is around 3.3 into 10 to the power minus 6, which is very less. So we can say that it is an yes, it is an electrically thin wire. That is, this 10-meter wire is very thin or very less compared to the wavelength of the signal, that is 3000 kilometers. Whereas the same 10-meter wire will not be electrically thin for a different signal, for a different frequency signal, rather for a higher frequency signal. Like we have a 10-meter wire for a 2 gigahertz signal. So for the 2 gigahertz signal, we will have lambda of the order of 3 into we can calculate lambda, and that will be of the order of few centimeters, like 15 centimeters here we have. And whereas this 10-meter wire is much larger compared to the wavelength of the wire, wavelength of the signal, right? So it is not an electrically thin wire. So then we were talking about the near field region and the far field region in an antenna. These are all the different aspects which we need to keep in mind while grounding. That we will come later, right? So an antenna, there are two, the area of influence of an antenna, it can be subdivided into two zones, rather two regions. One is the near field region and the other is the far field region, right? So that zoning also depends on the wavelength of the signal. So what is the general conception is that for distances less than the 1/4 of the wavelength of the signal, we consider it as a near field region. Greater than 1/4 of the wavelength of the structure, we consider it as the far field region, right? So now, if we see an antenna which consists, say, of multiple sources, a multiple source antenna, so there will be mutual induction between the different sources, and the field, the electric field till lambda by 4 distance, it is of disturbance type. That is, there will be overlap of the near fields in that region. And generally, this disturbance type field will not follow the Maxwell's equation. Whereas the far field, that is the field at a distance greater than lambda by 4, that follows Maxwell's equation. These are observations which have been pertinent observations which have been made from different experimental results. So for distances 0 to lambda by 4, that is the near field region, our electric field and magnetic field, electric field is not proportional to the inverse of square of the distance and magnetic field is not proportional to 1 by r. Whereas for d greater than lambda by 4, that is in the far field region, we have the electric field proportional to 1 by r square and magnetic field is proportional to 1 by r. That is, it is following Maxwell's equations. So now this grounding I was telling, this for suppose in substation grounding, we have a lightning impulse voltage which needs to be grounded. So for impulse voltage grounding, from 0 to lambda by 4, the first impulse starts developing and it stabilizes after this lambda by 4 distance. Now, before this stabilizes, since the frequency of the impulse signal is very high, and so the wavelength is very small, another second impulse wave starts developing, and that is about to strike. And this cycle continues. Thus, the effective wavelength for impulse grounding should be taken as lambda by 4 and not lambda. Any confusion, any doubts? You can stop me in between. Any confusions, any clarifications are required? Okay. So now we will be now we were discussing about the ground loops, right? So we have these ground loops which are connected in the soil, like two power equipments will be there and they will be grounded through a common resistance. This is what we call a ground loop. So suppose there is a fault in equipment 1. So that generates a fault current IF which circulates in the loop and it passes through equipment 2 also. And hence, since the fault current passes through equipment 2, it energizes equipment 2 and that will create a fault in equipment 2. So this is not what we desire, right? So we had a fault originally in equipment 1 and we wanted to ground it or we wanted to dissipate it to ground. But what happened actually is, again, equipment 2 gets energized and there is another fault current. So there is a propagation of this fault current between equipment 1 to equipment 2. So what we do is, while grounding, the basic practice is these grounding loops must be broken. So how can we break a grounding loop? So what is our aim here? We don't want the fault current to propagate from equipment 1 to equipment 2. So if we put a very high resistance in the path of the current, like here our soil we have put, if we put like that, then obviously the current reaching equipment 2 will be very small. So what we do is this ground loops are intentionally broken by some equipments like gravel, which has very high resistivity, right? So this case of grounding loops is very dangerous for electronic equipment, especially that is for signal grounding. So we have the electronic components in our control system, control rooms, right? So there also we need to ground the electronic equipment. So there this thing is more dangerous, this existence of ground loops, because electronic equipments will not be able to withstand that much amount of huge current, right? So that is the reason also we should never ever ground any power equipment with the signal components. That is, none of the components of the power, like transformers and transmission lines, should be grounded with the components of the control room. So next we were looking into the different properties of soil. So, so we need to understand that if we want to study grounding, just a second. So if we want to study grounding, we need to understand the properties of soil, rather the electrical properties of soil, the properties of soil which affect the proper flow of current through it, which affect the generation of electric field. So the different electrical parameters which are considered for soil, rather the parameters which considered for soil which affect the electrical properties or the flow of the current are listed, like the percentage of water, resistivity of soil, magnetic permeability of soil, and permittivity, electrical permittivity of soil. So if you see here, suppose a lightning impulse voltage is striking this ground, a lightning voltage or lightning current is striking the ground. So what will happen next? So this will create an electric field, which is shown here by E net in a particular direction, right? So this E net can be resolved into two components for our analysis purpose. One is the vertical component EV and the other is the horizontal component EH, right? So when a lightning impulse voltage strikes the ground, the field basically does not propagate in a vertical direction or a horizontal direction. Rather, the field actually deviates. So why this deviation occurs? This is because of the change in medium. So this soil is considered a multi-dielectric medium, right? So like we have suppose a light wave, and there is you have heard of refraction of light, right? So why the refraction occurs? Because there is a change in medium. Rather, there is a change in the refractive index of the medium from one medium to other. So here also, since there are different components inside the soil, different layers, multi-layers soil is present. So hence we have different permittivities in the different layers. And that actually deviates my electric field at every layer. Also, due to these different interfaces, this electric field undergoes multiple deviation. So due to this, soil will get polarized, and mainly it will undergo ionic and orientation polarization. So there are this polarization is entirely a different topic. I'll not bring the details in here. So basically, these ionic and orientation polarizations are two different types of polarization. Also, this behavior of soil is also a frequency dependent phenomenon, right? Why frequency? It is a frequency dependent phenomenon. I'll explain this. So like I was telling that soil is a multi-dielectric medium, right? So we have what is called this permittivity of any particular dielectric that is dependent on the frequency of the signal that is propagated. So till now we were maybe we were thinking of low frequency, that is power frequency. So we took this permittivity to be constant, but actually it is not constant. There are two components of the permittivity. One is called real permittivity and the other is called the complex permittivity or the imaginary component of permittivity, which is frequency dependent, and that is higher for higher frequencies. So as the frequency of the signal changes, the soil will behave differently. Thus, for a power frequency signal, soil will behave differently, whereas for an impulse signal or a high frequency signal, soil will behave as a multi-dielectric. Whereas for the power frequency signal, it might behave as a single dielectric. So up to this, is it clear? Any questions? Mr. Purushottam, Anushri, anyone?
Clear, sir.
No, sir, clear.
Okay. Okay. So next we were talking about the different generation of mechanisms of high voltages in the laboratory, like DC, AC. We have three kinds of voltages, right? DC, AC, and impulses. So DC is a constant magnitude voltage. AC is a voltage which changes its magnitude every half cycle. And impulses are special type of electric signals which have a very high rise, instantaneous high peak, and then it decays down. So we will look into the different mechanisms, or rather the different circuits for generation of voltages in high voltages in the lab, in the laboratory. So first we are taking up generation of AC voltages. So there are three mechanisms by which we generate high voltages in the laboratory. First is cascaded transformer. Then we have series resonant transformer. Then we have the Tesla coil. Okay. So first we were discussing about cascaded transformer. So if you see this diagram, I'll go through it once again. So there are three stages. You can see these violet windings. These are one stage. So S1 I have marked, S2 and S3. These are the three different stages. So which are cascaded together or which are connected in series. So we call it a cascaded transformer. So there can be different stages. There can be different number of stages in the cascaded transformer. It can be 3 stage, 5 stage, 7 stage. So accordingly, the output voltage will vary. So here, what is the basic principle, basic mechanism of the circuit? So if you see here, suppose we are applying a voltage of V volts in the primary of the first transformer. So this P. Okay. So here, actually, we are applying a voltage of V in the primary of the first transformer. So each transformer has three windings. One is primary, one is secondary, and the other is tertiary winding or excitation winding. Right. So this P, suppose we apply a voltage of V here. So here it will the ratio of the transformer is such that here a voltage here a voltage will come as V, and here also voltage will come as V. So if this is V, this voltage will be V. Okay. So if this is V, sorry, this is VI, sorry. Here we apply a voltage V, and the ratio of the transformer is such that here a voltage of VI applies, here a voltage of VI appears. If this is VI, this will be VI. If this is VI, again, the ratio is adjusted such that this one is VI, this one is V. Okay. Again, if this is VI, this is VI, the primary of the third stage. This is VI and this is V. So now you can see these red colored boxes, right? These are insulating stands. So here this voltage is V, right? So we cannot directly ground it. Hence, we put an insulating stand of V volts and we ground that. Again, here in the third stage, we have an insulating stand of 2V volts and we ground that. So the net voltage appearing at the output is 3V, right? So this is 3V. So we are applied a voltage of V and we get an output voltage of 3V. Hence, we have magnified the voltage or we are generating high voltage. That is, we apply a voltage of V and we get output 3V. Suppose you are applying 100 kV, you'll get an output of 300 kV. So basically, this is the principle, cascading different stages of the three winding transformers. So this is what we are doing. This is a small derivation that you can look into once again. So next, I will move on to the next topic. This was what we had discussed in the previous class. So now we'll be moving on to today's class, right? So any confusions, any doubts from previous class, anything you can ask? Any confusions, anyone? You'll be having the exam very soon, so prepare well. Those who have registered for the exam, obviously. Okay, so we had completed the discussion of this cascaded transformer. So now we'll be moving on to the next topic, which is Tesla coil, right? We'll look into the circuit of Tesla coil first, and then we will see how it operates. So if we see, you can stop me in between if you have any confusion. Okay. One second. First, I'll draw the circuit, then I'll explain. So this is the circuit for Tesla coil. So it is basically the core here used is an air core transformer. It is an air core. So hence, there is a loose coupling between the primary and the secondary. Okay. So I'll write them. I'll go on writing first. So basically, the Tesla coil is an air core transformer, and hence there is a loose coupling, right? Initially, what will happen? This S1 switch you can see, right? So initially, S1 is closed and C1 is the capacitor C1 is fully charged to the input voltage V, right? Is it clear? Okay. So now, as this capacitor C1 will get fully charged, then obviously it will find a path to discharge, right? So it will discharge through this path, through this inductor and resistor. So I'll write this. As the capacitor gets fully charged, as the capacitor gets fully charged to V1, it discharges then it discharges through the inductor L1. It starts discharging through the inductor L1. And once it starts discharging, there will be oscillations, right? Because it is you just ignore R1 for the moment. Then this is an LC circuit, right? So the inherent oscillations will start, and hence there will be oscillations. Hence there are oscillations. What will be the frequency of oscillation? Anyone? So since the discharge is happening between L1 and C1, the frequency will be 1 by 2 pi root L1 C1. So now the primary is fully energized. So here by primary, I mean the primary inductor, that is L1, right? So primary is. So basically what happens till now? C1 will get charged from V by closing S1. And once C1 gets charged, it will start discharging as S1 is opened and C1 will start discharging through this L1. So this will set up an oscillation in the primary side with frequency F1 equal to 1 by 2 pi root L1 C1. It's clear. Okay. So now next what will happen? So since the primary is energized now, and I told that it is a air core transformer, right? So there is very loose coupling. So this energy flows through the air with very high leakage flux and sets up energy in the secondary winding. So this energy flows to air which has very high leakage flux and sets up energy in the secondary winding. So now once energy is transferred to the secondary, this will initiate a current to flow in the secondary winding, secondary path also. So now this energy in secondary will cause a current to flow to inductor L2 and capacitor C2. Okay, so this energy is transferred here and there will be a current flow. I secondary will flow through L2 and C2. Ignore the resistances for the time being. Okay. So this energy flows through air from the primary, it is transferred to secondary. So now the load capacitor, that is, so this energy will flow through the air and it will set up a current in the secondary. This will also start another oscillations, inherent oscillations in the secondary winding. Oscillations in the secondary. With frequency F2 equal to 1 by 2 pi root L2 C2. Okay, so this will start. So this load, now we need to think of this load capacitor C2 in the secondary one. You can see here, right? This capacitor. This capacitor I am talking about. C2. This C2 is the load capacitor, right? So this can be air or it can be a sphere gap or it can be a toroid coil. So there is a particular voltage up to which the load capacitor can withstand. So as this energy is building up in the primary, then it is setting up in the secondary. So only up to a particular voltage it can withstand. So once the secondary energy crosses that threshold, there will be a flashover. there will be a flashover or there will be a blast of the capacitor C2. Due to this flashover, there will be heat, generation of heat and light, and hence some energy will be used up, and hence the net secondary energy will be dipping. There will be a dip in the net secondary energy. So now the energy in the secondary is less and energy in primary is more. So again, energy transfer will occur from, since there is a imbalance in energy, energy will transfer from secondary to primary. So this energy transfer cycle is very much lower. The amount of energy transferred in this cycle is much lower than the previous cycle, because the previous cycle there was transfer of energy from primary to secondary, and that was because of energizing of this inductor L1. So you need to understand this, you need to think carefully. So why this energy transfer is happening and why there is a flashover, and again now what will happen? So there is a transfer of energy from secondary to primary again. So again primary energy will build up slowly, and once it reaches peak value, it will be charged L1, and then again it will transfer to secondary. Again, once it transfers to secondary, there will be a second flashover occurring in the load capacitor C. And again, there will be a dip in energy of the secondary winding. And this cycle, this energy transformation cycle will continue. And this generates very high frequency AC voltages of high magnitude, high frequency. So this part I will write down quickly. So the load capacitor, you can also note down, otherwise this is theoretical, there you will feel bored. Please interact. If you have any questions, anything you can ask. Otherwise, this class only it is a monologue. Only I will talk and you will listen. So the load capacitor can withstand a particular up to a particular voltage. So once energy reaches the peak value, there is a flashover. Due to this flashover, are you able to hear? Are you able to see me? Am I audible?
Sir, audible, sir.
Okay, so there's a means internet got disconnected in between. Sorry. Screen is visible, right?
Yes, sir.
So what are you studying? Yes. So I'll write this down first. Some energy is used, hence net secondary energy dips. Now energy will be transferred from so now energy will be transferred from secondary to primary. And as the primary energy builds up, second. So as the primary energy builds up, again it transfers to secondary. Are you able to hear everyone? Are you able to hear?
Yes, sir.
The screen is visible or not?
Screen is visible, sir. Now it is not your notes, sir. It's members are showing.
Okay, okay. Now it is visible. Now it is visible. Now it is visible. Now it is visible.
Yes, sir.
The notes are visible, right?
Yes, sir.
Okay. Sorry for the interruption. There's some problem in the internet connection here.
No problem,
Oh.
sir. Sir, previous point we didn't return, sir. Once, please. Previous
Yes,
point.
yes, sure. So what is happening is there will be a transfer of energy from primary to secondary, and there is a load capacitor in the secondary side, right? So that load capacitor can withstand only up to a particular voltage, and once the energy level of the secondary crosses that magnitude, there is a flashover or there is a blast of the load capacitor. So due to this flashover, there'll be emission of heat and light. So some energy will be used up, and hence net secondary energy will dip. Now again, since there is an imbalance of energy between the primary and secondary, energy will be transferred again from secondary to primary. And now primary energy will again build up and it will again transfer to secondary. And this energy transformation cycle continues. Is this clear? Or should I repeat it once again, the entire thing? Is it clear, everyone? Is the principle of working of Tesla coil is clear to everyone?
Clear, sir.
Okay, so now we will do a small derivation about the expression of the voltage, output voltage for this Tesla coil. Correct. So I'll draw the circuit once again, otherwise these equations you cannot write properly. Yes, Mr. Anwar, why are you late?
Sorry, sir. Actually, I was in another meeting with office persons.
Okay. Okay, fine. Okay, so if you see this is the circuit diagram of the Tesla coil, and we will be applying KVL, that is the Kirchhoff's voltage law, in the primary winding and the secondary winding separately. Okay, so if you apply KVL in primary so here in this loop we are applying. Okay, so current I1 is flowing through C1. What will be the voltage? Can anyone tell what will be the voltage across C1 in terms of I1?
It will be same as V.
Yes, it will be same as V, but we want to write it in terms of I1. The current I1, we want to write it in terms of I1. So we can we write it like this? Is it fine? What will be the voltage across L1? Mr. Purushottam, can you please tell? Hello? Mr. Purushottam?
Sir,
Yes, can you tell me what is the voltage across L1 in terms of I1? Just normal circuit analysis.
okay.
Anyone? Anyone else? Anushri? What is the voltage across an inductor in terms of the current? Someone has to tell this. Mr. Ganesh? Yes, Mr. Purushottam, you want to tell something?
I'm not getting ideas.
So, okay. Suppose there is a resistor. Just think of this. There is a resistor R and current I is flowing through it. What is the voltage across it?
Sir,
I
L
get-
di by dt. Oh, sorry.
Yeah,
Yes. Yes, Mr. Anwar, you are correct. I'll just tell them. Okay. Okay, Mr. Purushottam, can you tell me there is a resistor R and a current I is flowing through it. So what will be the voltage across that resistor?
IR, sir, IR.
That is IR, right? For resistor, it is okay, I into R. So similarly, there is an inductor L and a current I is flowing through it. What is the voltage across the inductor?
IL,
Anushree?
IL, sir.
IL. Are you sure? Are you sure?
Sir, I into L di by dt.
I into L di by dt. You are very close, but it is not correct. It is L di by dt. Okay.
Okay, sir.
Okay. So, and one more thing, you tell me what is, suppose a capacitor is there, C, and a current I is flowing through it. What is the voltage across the capacitor? Yes, Anushri, can you tell? I have written it here. Check the notes. Just it is visible in front of your screen. What is the voltage across a capacitor? If a current I is flowing through it, for resistor it is I into R. For inductor it is L into di by dt. So for capacitor it will be
1 upon C1 integration of I dt.
yes. Yes. So you must remember these three things. Okay. So suppose we are applying there is a resistor is fine for everyone. That is Ohm's law, I into R. Just remember for inductor it is derivative. So it is L di by dt. And for capacitor 1 by C integral I dt. Okay. So now you tell me if I apply KVL in this loop, this primary loop, what will I first term I have written 1 by C1 integral I1 dt. What will be the next term? Anushri, can you tell? Are you getting this or not? Everyone. Just tell me this one. Mr. Purushottam, can you tell?
Sir, I1 into L di by dt.
Why I1 into what is the voltage across the inductor I told? It is L di by dt. So it will
Sir,
be L1 into di1 by dt. Correct?
correct, sir.
Plus another term will come which is due to this mutual inductance. This M you can see, right? So this is the mutual inductance between the primary and the secondary winding. So the voltage due to a mutual inductance is M into the opposite current, that is di2 by dt. So this is equal to V1. And now you tell me in the secondary side, you tell me, see this circuit and tell me what is the KVL in the secondary side.
One by C2,
Yes, 1 by C2
sum of I2 dt.
integral
Integral I2 dt.
plus
Yes.
wait,
L2.
next you wait. Next term, Anushri, can you tell what will be the next term in this equation?
So L2 di2 by dt
And then
plus M
hmm,
di1 by dt.
that will be equal to what?
V2.
There is no B2 here. It is shorted. So it will be 0. Okay. Okay. So these are the two equations in the primary and the secondary side, right? So now if you convert it to everyone, are you comfortable with the Laplace transform? Have you heard of it? Yes. Have you heard of Laplace transform?
No, sir.
Others? So don't know Laplace, then it will be difficult to do this derivation. Laplace transform, I'll give a brief idea. So basically here we have written all these voltages and currents in the time domain, right? So there is another domain which is called as frequency domain, right? We can express these voltages in terms of time as well as in terms of frequency. So this another domain, frequency domain, also we have the Laplace domain. In frequency domain, we have the Laplace domain, we have the Fourier domain. Fourier transform is there, Laplace transform is there. So basically, this t will be transformed to another variable in Laplace. It is called as S domain. Just I will write this. Anushri, are you comfortable with Laplace transform? Mr. Prabodh, no, Mr. Anwar.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So if I convert to, someone can tell me if I convert the first equation to S domain or Laplace, what will be the first equation? This first equation, this is equation 1 and this is equation 2. So the first equation converting to S domain, what I will get? Someone can please tell. Mr. Anwar, can you tell? Hello?
The S domain means Laplace domain, right, sir?
Yes, yes, Laplace. So the first equation converted to Laplace domain, what will be the first equation? Anushri, can you tell? Anyone else? Mr. Prabodh? Mr. Rakesh? No one. Okay. First equation I will write, second equation you have to tell me. Okay. So this integral of I1 converted to S domain will be I1 by S. So it will be I1 of S by SC1 and derivative is multiplied by S. SL1 into I1 of S plus and V1 is a constant. So Laplace transform of a constant is the constant by S. So similarly, can you tell me the second one? Second equation Laplace transform, Anushri? Just seeing this equation, you can tell me this second equation.
I2S, yes, sir. SC2 plus
What will be the next term?
SL2
Hmm.
I2S
Plus SM.
I1S.
Okay. So now we need to find out I1 and I2 and all the other terms are known to us. So we can form a matrix, right? So basically the above equations, if we write it in the form of a matrix, it will be like this. Then we have, here we have 1 by SC2 plus SL2 and SL. 1 by SC2. equal to V1 by S. 0. So now we have to solve this equation. So to solve a matrix equation, what is the procedure followed? We can use different procedures, but I will use this Cramer's rule, right? So what does Cramer's rule state? So suppose I want to find out I2 of S. So I will not describe the entire process of finding this one. It will take a lot of time. So once we have these equations, we can find out I2 and I1. And once we know I1 and I2, from that we can find out V1 and V2. Finally, the output voltage, the load voltage, we will get as, I'll write the expression in time domain. Otherwise, it will be very. So this is the expression for the final load voltage, the voltage across the load capacitor. So you can see it is a very high frequency voltage. And this alpha and beta, this will be some constants which will be appearing. If you take the Laplace and then inverse Laplace, you will get what is called this V2, this load voltage. Is it fine?
Sir, can we just go to the last slide once, please?
Yes. Any confusions?
The first equation, what we have written in KVL format. Right, sir. So we have taken the loop of the second mesh, right, sir?
Yes. Actually, I think, yes, there is a mistake here. Actually,
yes, sir. So it should be right.
Just a second. I will look into it. 1 second. Sorry, the circuit diagram is actually not correct. I'll correct it. Is it fine now? The circuit diagram I have drawn actually incorrect. The switch is in parallel. Here also you correct it. Here also I did it wrong. The capacitor is connected in series. Here I have the switch. Is it fine now, Mr. Anwar?
Yes, sir. Now it's okay. So we are for momentarily the switch is right now the switch is in off condition, correct, sir?
Yes. This is
S1 is
during the
0.
discharge. Yes, this is during discharging condition. We are writing the equations. Because the voltage will be generated during the discharge condition. Only this high frequency AC voltage that will be generated due to this repeated charging and discharging. We are taking in the first S1 will be momentarily closed and C1 will be fully charged. Then we will open S1. C1 will now discharge through L1, and this energy build-up in the primary will be transferred to the secondary through the air medium. And then again, there will be a flow of current in the secondary winding. And again, this transfer of energy cycle will continue. Okay.
Sir, there should be one in resistor also in this circuit, correct?
Yes, resistor should be there. But if I include resistor, these equations will be more complex. That's why I have ignored the loss component here. You
Sir,
can do it with resistor.
Sir, what about the internal resistance of this voltage source?
Yes, it will be there, obviously. If you want to analyze it, actually, it should be there. Everything should be there. Generally, what we do is we take this R1 total resistance of the circuit, we represent it as one resistance R1. So you can include that in the calculations also. So basically the form of the equation will not change. These constants and all will change. That is what will bring the difference. Fine, right?
Sir, it's good, sir.
Okay. Okay, fine. Next, we will move on to the next topic, which is, I think, it is series resonant transformers. It is the last uh, process of measurement, or we will do some numericals or something. Next class, we'll do the numericals. Today, we will complete the theoretical part. So series resonant transformer, that is basically another circuit which is used for generation of this AC high voltages. Okay, so okay, fine. I'll first write what are the circuit components. Then I will first I will draw the circuit. One second, I will draw the exact circuit. So this is basically the actual circuit of a series resonant transformer. Here we have the input and we are feeding it to a transformer, which is connected to an adjustable inductance and a load capacitance. Okay. So the equivalent circuit for this, if we simplify this circuit, the equivalent circuit, it will look like this: a voltage source, then we'll have the resistance, variable inductance, and the load capacity. So this is my equivalent circuit. So
Sir, can we see both the circuits in a single? Yeah, right.
yes. Is it fine? This is my load capacity. Okay, so is it fine, Mr. Anwar?
Yeah, right, sir. It's okay.
So basically, this circuit will consist of one, it will consist of a high voltage transformer, also called the test transformer. Second, it will have adjustable inductance. And third, it will have a shunt capacitance across. So this capacitance, that is a C2, this will consist of both the bushing capacitance of the transformer. The bushing of the transformer has some capacitance, right? So bushing capacitance plus the capacitance of test object. So this is generally used for, I'll describe the principle of working of the circuit. Just wait for a few minutes. Yes. So it is generally used for testing of cables, measurement of dielectric loss, measurement of dielectric loss. Then we have some capacitive load testings. Okay. So next. So now this circuit, if we look into, I'll describe the working. So this inductor, you can see it is a adjustable inductance or a variable inductor. So we will adjust this inductor such that a series resonance occurs. So series resonance condition, can someone tell? Mr. Purushottam, can you tell me what is the condition for series resonance? Mr. Purushottam, can you tell?
Sir, no, sir. I don't have idea.
Resonance condition, you don't know?
No, sir.
Sir, is it omega L is equal to 1 by omega C?
Yes, it is correct. So, Mr. Purushottam, you have not done BTech, no? You're from diploma background, I think.
No, sir. I'm an ITA student, sir.
Okay, okay. Okay, fine.
Okay, sir.
So this might be little difficult for you. Are you finding it comfortable, these explanations? Because I am explaining from the perspective of a BTech student at least. Are you finding it
Sir,
comfortable?
I am after that. I'm reading some other books, sir, and I'm searching in net.
You tell me if you face any problem. Okay.
Okay, sir. Thank you.
So basically here series resonance will this adjustable inductance, we will vary that inductor and we will set it to a value such that the omega L is equal to omega 1 by omega C. That is the inductive reactance and the capacitive reactance is equal. So at resonance, what happens? There will be a huge flow of current, and that huge flow of current here in the series resonant transformer, it will be limited by the circuit resistance. That is the resistance of the connecting leads, which we have represented here in the circuit, in the equivalent circuit by R. That is the resistance R. So the if we apply a sinusoidal voltage in the input due to this series resonance, since the net, if you see here at series resonance, what will happen? Omega L will be equal to omega C. So what will be the net impedance of the circuit? Basically, it is R plus omega L minus 1 by omega C, right? So it will be basically R. So we will, during series resonance, we'll have a resistive circuit. And hence we will get whatever voltage we apply, that is sinusoidal voltage, we will get an exactly sinusoidal voltage, purely sinusoidal voltage across the test object. So under resonance, I will do this, I'll write this under XL will be equal to XC, that is omega L equal to 1 by omega XC. Net impedance is R plus XL minus XC. So at resonance, net impedance Z net will be equal to R. So it will be a purely resistive circuit. So what will be the output voltage? That is V out will be equal to the capacitor voltage, right? So it is basically the current, that is V by R into XC. So it is V by R into 1 by omega C. So it is V out is equal to, so omega L is equal to 1 by omega C, right? So it will be V by R into omega L. So basically this factor, omega L or 1 by omega C, both are equal, right? So that is the quality factor of the circuit represented by Q. So we can write it is equal to the output voltage is Q into V. So what is V output? Is basically quality factor times the input voltage of the circuit. So this quality factor we can adjust it, right? Where Q is equal to quality factor of the circuit. And this range is typically from 40 to 80. Okay. So V out now it can be varied. We don't have any control over the inductor at the capacitor here, right? Because at the resonance condition, capacitor is fixed because there is the load capacitance and the pushing capacitance. We can only adjust inductance, and we adjusted the inductance such that XL is equal to XC. Now we cannot anymore adjust inductance or the capacitance. So V out is given by Q into V in. So how we can increase the range of the voltage V out? That can be by varying the input voltage V. Okay. So also like first, what is the first step? We will adjust the inductance, right? So once we adjust the inductance to make omega L equal to 1 by omega C, we can also adjust this omega, right? That is the frequency of the signal. So by adjusting both omega L, we can fulfill this condition, and also we can vary the Q, which is omega L by R or 1 by omega CR. Sorry, here I had made a mistake. So this is basically omega. This is basically Q. Is it fine? Q is basically omega L by R or 1 by omega CR. So we can vary the, so now we can write V out can be varied by varying input voltage V or the inductance. Thus, actually we are varying quality factor. So suppose, so if Q is equal to say 40, so basically V out will be 40 times of V in. So we are generating high voltage AC. So suppose we are applying 1 kV, we are getting an output of 50 kV, right? 40 kV. So that is actually generation of high voltage.
So this Q is fixed for a circuit.
No, it is dependent on the circuit components I have written, right? Omega L by R and 1 by omega CR. You can vary that by changing the circuit parameters, the inductance. Basically, here you can only vary the inductance because resistance is actually fixed because it is the resistance of the connecting leads, connecting wires, and C is that capacitance of the load or the test object. So that is also more or less fixed. So you can only adjust this inductance.
Correct, sir.
Anything else you want to know? Anyone? Is it fine? Is the explanation fine? You understood how we are generating using just exploiting this resonance condition, which we have studied in our, say, in the network theory subject, how we are able to generate this high magnitude of AC voltage. Is it clear, Mr. Purushottam? Anushri, Rakesh? Everyone, is it clear?
Clear, sir.
Okay.
Sir, you told me
So-
that, sorry to interrupt, sir.
Yes, yes.
Yeah,
Tell me.
sir, this particular circuit is used for testing cables, right, sir?
Hmm.
So
Yes.
usually what we do is a high pot test for cables before using it in any entities. So is this particular circuit used in this high pot testing itself?
Hypot testing, I'm not familiar of. Can you explain? Can you tell me what is that actually? Then I can help you out.
Yes, sir. So there are two types of testing that we usually do for cables. That is,
Okay.
one is the measuring. I think everybody is
Yes.
yes,
Yes.
right, sir. So that is very common. But
Hmm.
if the cable is not in use for say 3 to 4 years continuously, or
Okay.
the cable has been made a cut in between for use it in a different purpose, then we do this hypot test, and
Okay.
these hypot test kits are usually available from 45 kV to up to 90 kV. And we apply 230 volt AC supply into it, and we get an output of around 40 kV.
Okay. Okay. Yes, we can do that. I think. I'm not sure what is actually done, but yes, we can use it in the hypot testing also.
That's
Okay.
So the hypot testing is using for insulation measurements.
Okay. This is also basically why we are testing. What we are actually testing in the cables, we are testing the insulation only.
level is only being tested over here, right, sir?
Yes, yes, because we are representing this test object as a capacitor. And what is this capacitor? The cable we are representing is a capacitor, means the insulating property we are actually testing. Is it not? Okay. So we'll do a small numerical. Everyone should try this out. So we have a say series resonant transformer. I'll write the question. Everyone please note down. A series resonant transformer. Turns ratio is 1:10. Is being fed from a 230 volt sinusoidal supply. So a series resonant transformer 1:10 transformer is being fed from a 230 volt sinusoidal supply. The resistance of the leads is 2.5 ohms. The load capacitance 2 microfarad. Find the maximum Can everyone try please this question? A series resonant transformer, it is 50 hertz. Okay. Can you please try this question, everyone? Just 5 minutes I'll give you, try everyone. From what I had described, from whatever I have described, it is there. Mr. Purushottam,
Yes, yes, sir.
please try this question, okay, everyone.
Sure, sir.
First try to draw the circuit diagram and then you will be able to solve. 5 minutes I'll give, then I will solve. Can refer to this circuit. Could anyone do? Anyone could do? Anushri, did you draw the circuit? Did you draw the circuit? Mr. Purushottam, Mr. Anwar, Anushri?
You have drawn the circuit, sir. I have drawn the circuit.
Okay. So can you proceed? Can you proceed next for finding this output voltage? Here we are applying 230 volts, right? What will be the output voltage in the secondary, Mr. Purushottam? What will be the voltage here? Mr. Purushottam?
Sir,
Yes, so we have a 1:10 transformer, and in the primary we are applying 230 volts. So what will be the voltage appearing in the secondary? Miss Anushri, can you tell? What will be the voltage in the secondary? It is a 1:10 transformer, and we are feeding it from a 230 volts.
2300.
Yeah, so it is 2300 volts. So R is given here, right?
It will be 920 amps, sir.
Output voltage I asked. How did you proceed? Can you tell? How did you proceed, Mr. Anwar? Can you tell?
So we have to make it a series resonance.
Yes. So what is missing here? First, what we need to find? L is not.
L we have to find sound.
Yes, yes. So at resonance, the condition we will use XL equal to
Omega
XC.
L is equal to, yeah. Right.
Yeah. So it is basically omega L equal to 1 by omega C. So L will be given by 1 by omega square C. So omega is 2 pi into F. C is 2 micro. How much this is coming? Did anyone calculate? Have the calculator here. How much this is coming? Can anyone calculate and tell me?
Sir, it is 5.066.
5.066 Henrys.
Yes, sir.
I did not calculate. Anyone else calculated? 1 second. Correct. It is around 5.07 Henries. So now can you calculate what is output voltage? It is Q times input voltage, right? What is Q? It is omega L by R into P input. Omega is 2 pi into 50 into 5.07 by R is how much? 2.5. What is V in? V in is not 230 volts. It is 2300 volts, right?
230.
Yeah, because we are feeding the transformer, we are feeding the circuit series resonant transformer with this 2300 volts. So how much it is? Tell me. How much it is coming? Coming around 1. It will be around 1.46 megavolts. This is the maximum voltage. We'll have a sinusoidal voltage with this peak value. Is it clear? Is this clear? Anyone else? Anyone? Any confusion, Mr. Purushottam?
Clear, sir, got it.
Anushri, is it clear?
Clear, sir.
Okay. So next we'll take up a small topic. 10 minutes more we will spend. So how we can realize these Tesla coils in practice? So we discussed about Tesla coil, right? How we can generate the high frequency, high magnitude AC voltages. So basically there are two types of Tesla coils. Number one is it's a radial Tesla coil. And second one is known as helical Tesla coil. So we have basically two types of Tesla coil. These are required. Okay, so we have basically two types of Tesla coils in practice. One is called the radial Tesla coil and the other is called the helical Tesla coil. So first I will draw the diagrams for both. Then I will explain. So basically in radial Tesla coil, So this is the radial Tesla coil. We have basically this iron bars or the coil which make up the which actually make the coil. We have the radial Tesla coil. Then we have what is called helical. Actually, it is difficult to draw. Right. So we have the coils here which are arranged helically, that is in a spiral manner. Once again, we will discuss in the next class about this radial and helical Tesla coil. I'll just draw the diagram. Next class I will explain. Okay. So these coils are connected like this. Okay, so next class we will discuss about this radial Tesla coil and helical Tesla coil once again. And okay, is it fine? Any confusions? Anything? So, Mr.
No, sir.
Purushottam, you had told to discuss about transmission line protection, right?
Yes, sir.
So next class will be the last class. So you can prepare the entire subject and you can come up with your doubts, anything. If anyone is registering for the exams, so you can ask me your doubts and I will continue whatever I was teaching. Okay.
Okay, sir.
Okay, fine. Anyone
Sir,
else? Yes.
Yeah, sir, the links that we are getting of the previous classes,
Hmm.
these are not whatever you are telling us in these classes, right? These are from Subba Rao sir's assignments that are being uploaded over there, correct?
No. Links, what you are getting? This is what I am describing. These links only you will get. But classes will be different. Actual classes are different. That is in the NPTEL portal. That is being handled by Subba Reddy sir. I could not get you. What you are telling?
No, what I'm asking is whatever you are teaching us in these 2 hours classes every week,
Hmm.
this is being recorded somewhere, correct, sir?
Yes. I'm sending that to NPTEL people. Are they not sending it to you?
No, sir, I am not getting that one. I am getting the general links where Subba Reddy sir is giving the classes, the lectures.
Are you there in the WhatsApp group?
Yes, sir, I am there.
I had posted. Okay, after you joined. Okay, I will post both the notes and this recording links. I will post it again today.
Yeah, please, sir. Thank you.
Okay. Anything else? Any confusions? Any doubts? Okay, fine then. You prepare well for the exam. All the best. Next class we will meet.
Thank you.
Thank you, sir.
Thank you.